Hey folks, okay, just one last session on our parsing aspects and just kind of a roundup of different things that we want to take into account and talk about a little bit. We won't get into most of these in detail. Maybe we'll come back and visit some of them towards the end of the term if we find we have a little bit of spare time. But again, these are just things to kind of wrap up our parsing session before we get on to the context sensitive stuff. All right, there are a couple of other grammar types that are available, so we'll talk about them just a little bit, the SLR and LALR, so we'll talk about those again in a sec. So we want to introduce a couple of those. We want to think about, if we've got all of these different parsing approaches, what's the right one for me? What's the one that I should be using for, project X? We haven't talked too much about the error handling and error recovery side of things for our parsers. And if you're writing a compiler, obviously you want to be able to give the programmer decent error messages and not kind of completely crash the first time something goes wrong, the first time you see a syntax error in the program. Some things that are going to crop up are cases where you actually need context-sensitive information to get the parsing right. And so we'll talk about where that can crop up. We've looked at a little bit of left versus right recursion so far in our grammars, depending on, we talked about left recursion for our top downs and right recursion for our bottom ups. And there's also the issue of what can we do in the way of optimizing our parsers as well. So these are just a few of the things that I want to touch on in this last session. So the idea for these two additional grammars that we'll mention, the SLR and the LALR, is that they produce smaller tables than the LR ones, and so there are some advantages there for the same sets of languages. So essentially, the SLR are ones that can eliminate the need for look-ahead, and so you can get a smaller table just because you don't have to have all this look-ahead information encoded in them. Whereas for the LALR, they have the advantage of identifying critical versus non-critical states. And the idea is a state is not critical if you can derive it from the critical ones. And so they only encode information for the critical ones and assume that as it's running, it can derive the other states that it needs. So again, you can compact your table there. If we've got some time at the end of the term, I would like to come back and look at the two of these in a little bit more detail, but I'm not sure how our timeline is going to go just yet. Okay, in terms of picking an approach, right? Somewhere along the line we want to decide which, top down, bottom up, do we want to do recursive descent? Do we want to do some kind of look ahead? What do we want to do? So in terms of if we're looking at a handcrafted choice versus versus some kind of a generated approach versus a scanner generated or a direct code generated or table driven generated, we might be able to provide some better error handling and more specific optimization if we're using the handcrafted approach. Right? We can go through and take extra knowledge we have about the language that we're working with and encode error handling that we know is going to be useful for the kinds of things we expect to see. Or we can include optimization that we know is going to be particularly effective. So the trade-off there is what we can do in terms of getting better performance or more suitable behavior versus the fact that if it's auto-generated, right, somebody's already produced the tool for us that can auto-generate our parser. It's obviously much easier to use their tool as long as it's reliable. And again, if their tool is reliable, we can pretty much trust what's coming out of it. Whereas if we're doing development by hand, we've got a lot of testing and a lot of debugging to do because obviously we can't trust our results until we have tested and debugged them. So it's just that trade-off. And when it comes to looking at a particular approach, again, are we going to go top-down or bottom-up? If we're taking a top-down approach, recursive descent is probably a better fit for the hand coding, where we go through and create our own function for each of the different kinds of components we're going to parse. In terms of which of these grammar sets we want to use, again, if we've got a tool that we're using to auto-generate whatever, that tool might have a lot to say in terms of dictating which one of these grammar approaches we're actually going to work with. But I'll leave that part for the moment. Again, error checking and recovery is going to be fairly critical for any compiler we want to be relatively usable, right? We want good error messages that provide a good idea of the context and the kinds of things that programmers are likely to mess up. So, if an error is found, if the programmer misses a semicolon or whatever it is, ideally we would like the compiler to be able to go, that's probably a missing semicolon, and to continue on and do the rest of the compilation and give informative error messages for the rest of it as well, and not just kind of quit the first time it sees the simplest syntax error. So we would like to see if there's a way that we can go ahead and do that. And this is where the idea of follow sets come in. Right? If I know that, for instance, if I'm using something like look ahead, and so I've looked at the next character and I've decided that this is the rule that I'm supposed to be using, right? I'm supposed to be expanding this particular grammar rule. The non-terminal tells me what kind of a component it is I'm trying to translate right now. So I've got context information or structural information. We're in the middle of a function definition. I can look up what the name of the function is that I'm trying to create a definition for. I can keep track of what line I'm on and what column I'm on in the line. So I can give them information based on that. In function in the function definition for foo on line 27, column 12, an error happened. Well, if I've got that follow set, then I can tell what kind of token is supposed to come after the thing that has the error in it. And so my compiler can say, well, this thing's obviously broken. What I'm going to do is try and skip ahead to something that tells me when I'm out of this broken thing, and I'll try and resume compilation there. So I can give you error messages on the rest of the stuff. Obviously the program's not going to compile because we've got this error in it that needs to be dealt with, but that doesn't mean I can't give you information about what's going on in the rest of it. So this is where the idea of follow sets, again, comes in fairly handy. Now, just in terms of customization, as we mentioned before, the idea of taking a hand-coded recursive descent parser means that at each step of the way, I'm writing, for instance, a parser for function definitions, right? A parsing function for function definitions, for instance. As the developer, I can look at this and know what kinds of things are likely to go wrong and what kinds of error messages and what kind of recovery I should try and invoke. So you can often come up with really good opportunities to customize your error messages and how you'll recover from them based on what it is you're trying to translate right now. So again, these are things that we want to think about when we're going through and developing our compilers, or when we're developing our parsers for the use in the compilers. Now, there are times when we can't just purely from parsing, from context-free parsing, where we can't tell what we're supposed to be doing next. So if you think about it, if there's a particular keyword that can have different meanings, then we have to figure out some way to decide what's the right meaning to use here. So this is one of those cases where we've got context-sensitive information coming in. So it might be the case that when we're building our parser, we're actually kind of combining it with the context-sensitive information and making use of that where we can, looking things up in the symbol table. It's also possible that what we can do is, if I know there's a scenario like this, if I know that the word foo can have these two different meanings, then maybe in terms of my parsing, I just say, well, the non-terminal for this kind of foo construct can have either one of these different forms. So you have some non-terminal to represent this kind of dual form, and then you leave it to the context-sensitive analysis stage to figure out which one of these is the correct one and to deal with it then. So you kind of push off handling of this until you're doing your context-sensitive analysis. So we mentioned the ideas of left versus right recursion in our grammars. Again, for the most part, we'll look at right recursive It should be left recursive for our top-down, and our bottom-ups can work with either left or right. We looked at it in the context of right for the bottom-up. This is going to have implications for the compiler writer, in terms of, obviously, if you're looking at your grammar, is left recursion going to be a problem or not? Left recursion tends to support left associative operators easily, whereas you have to jump through some hoops. And right recursion naturally supports right associativity, so you've got to jump through some extra hoops if you want left associative operators. There are some other considerations with respect to left or right recursion. Left recursion can actually give you a smaller stack depth when you're going through and doing your parsing, but we'll leave proofs and discussion of that again to a later stage if we've got the time as we get to the end of the course here. And then there's the optimization issues to consider, right? We've got the optimization layers in the parser itself, but we've also got the grammar that we're starting from, right? If we've got a more suitable grammar, we can produce a more suitable parser. So can we actually optimize our parsers by optimizing the grammar that it's working from? So can we do things like, take equivalent rows and equivalent columns in whatever we're working on and collapse those in a table? Is there a way to optimize what we're doing, to retain optimized information? Can we make use of table information to improve our direct coded approaches? Right? For whatever style of implementation we're looking at, what can we do to try and optimize our behavior based on that? So again, if we've got time, I feel like I'm saying that a lot. If we've got time at the end, we'll come back and consider these as extra topics towards the end of the term. All right, I will leave that for now. What we'll get into in our next few sessions is looking at the context-sensitive side of things. So beyond going just for parsing the straight structure of our tokens, now we'll get into actually doing some real checking of them.